One. Okay, and we're live. And looking at acids and bases, and mainly two different ways of looking at acids and bases. Okay. Um, and that'll make more sense when I get into it a little better. So, look at acids and bases, look at conjugate pairs, because as you probably are well aware at this point, chemistry is all about balancing things, very similar to mathematics in that way. But we're going to have balancing again, and acids and base pairs and their conjugate acid and base pairs on the other side of the equation. Okay. And I'm going to look at, first of all, the dissociation of different types of acids. Not so much Le Chaltier. I can probably take that objective off. I'm not going to really touch on that. And then I think what I'm going to spend most of our in-time class doing next week is looking at pH and how its relationships of basically the concentrations of protons in a solution and what the pH scale is actually doing, and then some useful numbers to look at around pH. Okay. Okay, so acids, from Latin word acidus, which is sour, which that'll tell you something about how acids were initially found, is when before we had lab instruments, we had our bodies to test things, and if we tasted something that was sour, it was acidic. Okay, and basic things are chalky or bitter. Okay, the original lab equipment was our tongues in this case. And first of all, we're going to look at the definition of Brønsted. I'm not quite sure what that O with the line through. I think it's Swedish. But anyway, Brønsted-Lowry, acids and bases. Okay. And also Arrhenius, acids and bases. So we're going to look first of all at Arrhenius. And Arrhenius is something that contributes hydrogen ions, protons, in water. So in this case, we have hydrochloric acid dissociates in water to hydrogen ions and chloride. Okay, so we've balanced our charges and we have a balanced equation producing protons. Okay, Arrhenius acids. Son of a gun, that's right. I did it again, didn't I? Okay. And you didn't miss much until the Arrhenius acids. There we go. So here we have our balanced equation. Hydrochloric acid, according to the Arrhenius definitions, contributes this proton here and this chloride, and a balanced chemical equation, balanced charges, and with an excess of protons on the right side, we have an acid. Okay. They're sour, of course. Like we said, it will turn blue litmus paper red. Okay, so litmus paper. There are questions on litmus paper. And of course, basic things keep blue litmus paper blue. Basic for blue, right? So the naming conventions for acids is a little funky. I'm going to go over them somewhat quickly, just kind of get your mind familiar with these words. But it's really, to me, I always found it just memorizing them and looking at the structure and knowing what that is, sort of like learning a language. There are rules, but I think they're overly complicated. Okay. So if you have an acid, okay, giving up protons with a nonmetal, we have the hydro with ic, so hydrochloric acid. Okay, acids with a hydrogen ion and a polyatomic. We all remember our friends, the polyatomics, like right here. There's the polyatomic portion. of that molecule. You change the end of the name of the polyatomic ion from, if it's an 8, several weeks back, to an ic. If it's an ite, okay, to an us. So we have chlorite and hydrochloric acid, and chlorite to chlorus. Sorry, I even confused myself a little bit. Chlorate to chloric acid and chlorite to chlorous acid. Don't worry about it. Again, I'm just exposing you to these words. And there are handy charts at your fingertips to help you find the actual names. But the important thing, if you look, this shouldn't look completely foreign here. We have anions here and a whole bunch of polyatomic anions over here. Okay, and their associated names. The us's and the ics, essentially, in this case. Okay, so for instance, in this first case, we will have hydrobromic acid. Okay, and carbonic acid in the second case, and bromous. Look ahead. Yeah, bromous acid in the third case. So even after all this time of me looking at them, I can still get thrown off by the polyatomics. Okay. K-hydric. Okay, so that's what an Arrhenius base is. An Arrhenius base is something that in solution is releasing or contributing hydroxide ions, which is this OH negative moiety that we've seen several times. They are, like I said, bitter. Okay. And of course, there are electrolytes because you have anions that are released in water. Okay. They are soapy. So your soap that you use every day, hopefully, well, every day is soapy, slippery, primarily because of it is a basic solution that you're using. Okay, and litmus paper turns blue or stays blue, I guess, when it's dipped into a basic solution. Okay, so you have sodium hydroxide in solution. Dissociating into a hydroxide ion and sodium. Okay. And we have an Arrhenius base with sodium hydroxide as an example. Okay, so that should look familiar. I'm assuming probably more familiar to you than to me. So they just named hydroxides most of the time: sodium hydroxide, potassium hydroxide, barium hydroxide, and aluminum hydroxide. And that's calcium hydroxide being used as a filler in root canals. I think that's a filling, right? Correct me if I'm wrong. And then, this whole, so that is what do you call this again? You can tell me. Is that a root canal? Oof. Okay. Fun. So a couple fillings of root, 3 fillings in a root canal. See, I'm getting it a little bit. So calcium hydroxide, slaked lime's the old-timey name for it, but calcium hydroxide. Okay, so I'm just going to run through these somewhat quickly. Again, exposure. So I have a nitrous here, so you can look through here. We have a nitrous acid. Okay, calcium hydroxide, which we just saw. Okay, hydrogen, and with that sulfur. So we know we have sulfuric acid. Okay, an iodine here, iodic acid. You can see how I kind of pick through these things. And sodium hydroxide, of course, that one. Hydrochloric acid, sodium hydroxide will show up pretty easily. Okay. Good. Okay. So Let's keep these. So Arrhenius acids. I'm not going to write the whole thing. Protons gives you your acid. Okay. And hydroxides give you your bases. Okay. So the next way we're going to look at acid is the Bronsted-Lowry. Bronsted-Lowry. And Bronsted-Lowry bases, same type of idea, just more useful in a lot of situations. Then acid is something that donates protons, okay? And a base is something that accepts protons. Oh. Okay. So a proton donator is an acid, and a proton acceptor. Acceptor is a base. Okay, so let's see what that looks like a little bit. It seems sort of esoteric, I guess, at this point. Let's see, I'm going to try to be a little bit fancier. So we have hydrogen chloride, which we know is a base by looking at the previous slides. In water, the hydrogen chloride dissociates and gives off, there we go, a proton. Okay? And the hydrogen accepts that proton. So we get hydronium and chloride. So let me. Okay. So we have the Bronsted-Lowry acid here and the Bronsted-Lowry base. Okay. So what that sets up is that you have on the other side the conjugate acids and base. So now chloride becomes the base. Okay. And hydronium, H3, is the acid. So we have the conjugate acids and bases balancing out the equation. Okay? So at the base, if we look at it from this side, the chloride would accept a base if we run the equation the other direction. Okay? And the hydrogen chloride is the acid, which donates the base. Okay? And likewise, in this case, water, H2O normal water, accepts a proton from hydrogen chloride and is the acid, or excuse me, is the base, the acceptor. And then the hydronium ion, running the opposite way, would then become a proton donator and become the acid. Okay, on the left side, we have the acids and bases. On the right side, we have their conjugate acids and bases. So let's look at another one here. Oh, carried away. Ooh. Okay. So in this case, ammonia and again water, but you're going to see something interesting. Okay, so this is the Bronsted-Lowry base over here. That makes this the Bronsted-Lowry acid, the conjugate acid of ammonia. And we have now water becomes Bronsted-Lowry acid. And the hydroxide ion is the conjugate base. Okay. Okay. So we have the conjugates acids on bases on both sides, okay? Based on where the protons go. Yeah, so far so good? Okay. It's sort of a simple concept, but people can get confused, and you probably will get questions. In fact, I know you will get questions being able to pick out the Bronsted-Lowry acid and on both sides of the equation. Okay. Okay, so to review, if we're looking at acids and bases as in the Arrhenius form, whether or not they produce protons or hydroxy molecules determines their acids and base, and Bronsted-Lowry is a donation. We're just looking at the protons. Okay, hydronium, and whether they are either proton donators or proton acceptors. Okay, so you tell me, we're going to look at these two chemical equations. Let's do it all the way back. Let's do a little on-the-fly review here. First of all, are they balanced? And second of all, which one is the Bronsted-Lowry acid and base on the left-hand side? Okay, so we have 1, 2, 3 hydrogens on the right, or on the left, 3 on the right, 1, 2, 3, 4 oxygens, 1, 2, 3, 4 oxygens, 1 nitrogen and 1 nitrogen. So we have a balanced equation. Okay, so is the nitric acid the acid or the base here on the left? Okay. Yeah, we'll do that. Do this little move here. There, I got a spot for it. Okay, so of course, this is the Bronsted-Lowry. The proton donor is the acid. Okay, so that makes this the Bronsted-Lowry base or the proton acceptor, and their conjugates are Bronsted-Lowry acid and the Bronsted-Lowry base. Okay, so likewise, let's look down here. Hydrogen fluoride, weak acid. Happen to know that. Bronsted-Lowry acid. That makes the fluoride part of the conjugate base. And we have the acid and the, oh, I messed it up. And the base, and of course the acid. Okay. Acid, base, and their conjugates on the other side is what I added on there. Okay. Okay, so the sours are the acids. Hydroxy, especially if we're looking at Arrhenius, is a base. Chalky is basic. It's an electrolyte. Okay, both are electrolytes. Okay, and produces acids. That's an Arrhenius, or excuse me, protons. It's an Arrhenius acid, of course. And kind of the last thing we'll look at before I release you to do your homework. And then we have a nice start on class for next week. Yeah, it'll be everybody's last class on Tuesday. So we've already seen hydrofluoric acid, looked at it as a Bronsted-Lowry acid. Okay, it is a halogen. That should ring some bells. And is a weak acid. The rest of them are strong. Okay. And the difference between a strong and a weak acid is this. Just like when we were looking at solutions, the strong dissolution and weak electrolytes and strong electrolytes, strong acids and weak acids, hydrochloric acid in water will completely dissociate for all intents and purposes into hydronium and chloride. And a weak acid, which is indicated by this arrow going in both directions, meaning that in solution you still have some of this chloride on the left as well as some hydronium as well. So you have both. In the first case, completely dissociates into what's on the right. And in the second case, you end up with a balance. Okay. HA. Oh, so a strong acid completely dissociates. Yeah. And here is a list of the hydroiodic acid, extremely strong acid. Interestingly, I always thought that was interesting that hydronium ion is a weak acid. Okay. You would think that extra proton would come off willy-nilly, but there are things that are much more acidic than that. Hydrobromic, perchloric, hydrochloric, sulfuric, all those are strong as you move up the chart. And you notice, and I'm going to circle back to this. Down at the bottom, we have water listed as a weak acid. Okay, so what that should tell you in your mind that just distilled water sitting out on the counter, sitting out at room temperature, will have some dissociation of the water molecule itself. It's not going to be 100% H2O. Okay? And then weak acids, like I said, we end up with a balance between the weak acid on both sides and hydronium ion. Conjugate acid, conjugate base, base, conjugate acid, and there is a balance on both sides of that to give that weak acid. Okay, same thing. So weak acid, so right down here on water, put that way in your memory bank because I'm going to return to that concept when we look at pH. Total dissociation in a strong acid, hydrochloric acid, into hydrogen and chloride. And then the last thing we'll look at here is strong bases. Exact same concept, but instead of dissolving or dissociating into hydronium and its pair, we have hydroxide. So potassium hydroxide, okay, is a strong base that dissociates into potassium and hydroxide ions. Okay. Okay, lithium hydroxide, sodium hydroxide, potassium hydroxide, all those are contributing, and we're back to looking at Arrhenius bases as a definition here because it contributes hydroxide to the solution. So, and I don't expect you to know these, memorize these, but the concept that there are strong and weak acids, strong and weak bases, and that you know that you have a chart that will tell you whether or not there's a strong or weak basis. So hydrogen bromide, strong acid, the strong acid. So hydrogen bromide, strong acid, sodium hydroxide, strong base, hydrogen sulfide, strong acid, and then we have a weak acid in a nitric acid, nitrous acid, sorry, and a weak base in copper hydroxide. Okay. And how are we doing here? Okay, so we'll circle back and review this. Yeah, on Tuesday. That's a good stopping spot for us, actually.